Hi everyone, welcome to this week's astronomical talk. Tonight we're very honored to have Professor Moira Jardine with us to give a talk titled Trouble with the Neighbours, Outpouring from Young Suns. Before we begin, here's a short introduction about our speaker. Professor Moira Jardine is currently a professor of astronomy at the University of St Andrews. She was also appointed to a personal chair in 2010 when she became the first female professor of physics at this university. Among all the other highlights, Jardine chaired the 2008 Cool Stars conference called Cool Star, Stellar System, and the Sun, hosted at the University of St Andrews. This was the first time this conference was held in the United Kingdom, which is pretty cool, and around 350 international astronomers were in attendance. The Royal Society of Edinburgh awarded her the Young Persons Award in 2002 for outreach work with young people in local schools, encouraging participation in the sciences. She was elected a Fellow of the Royal Society of Edinburgh in 2013. And during our talk, if you have any questions or you have answers to Professor Moira's questions, you can put it in the group chat. Now, without further words from me, Professor Moira Jardine, please.
Yes, so don't imagine that you're going to have a comfortable time while I'm talking. I've got test questions for you all, just to keep you on your toes. So I wanted to start off by explaining a little bit about the image that I have here. What you're seeing here is a young planet and a young star, and the planet's atmosphere is being lost as a result of the outpourings from this star. And so my talk is about the efforts or the things that are important to a young planet if it wants to hold on to its atmosphere, if it wants to be habitable, and the impact that its parent star might have on that. And as will become clear through the talk, not all stars are very good neighbours. But before I get into my talk, I wanted to show you a picture. Hopefully I can get this to advance. There we go. Of the team at St Andrews, because science is not done in isolation. We all of us work in teams. So I thought I'd start by introducing you to the youngest member. This is Ollie, and his mum Rose. Rose is doing a PhD with me. She's doing it part-time because the rest of the time she's running after Ollie. Here's Sarah Fowler, who's in her second year. Sarah was an undergraduate at St Andrews, so she is one of the local students, if you like. And down at the bottom left here, we have Clara. So Clara had a career as a professional programmer before doing her PhD. She was a software developer for NASA, and she's just started. She's just in her first year. And here we have Simon Daly Yates, who's a postdoc, and Simon shows this picture of himself because he said that this exemplified his approach to programming. And I wasn't sure really whether he was more serious about the power tool or the bottle of wine. And here's me. I'm just a cartoon figure because I reckon that the four people in the rest of my team are the ones who really do the heavy lifting. So let's get started by thinking about the young stars that I'm going to talk about. And so this is my first question for you all. This is quite a well-known group of stars. So can anyone tell me what the name of this group of stars is? I'll be very impressed if anybody gets it, by the way. You can stick it in the chat, and Lehan can maybe just shout it out for me because I'm not sure I can get the chat window up while I'm talking. Has anybody got the answer? Oh, this is shameful, Cambridge, you know.
3 people answered. It's The
Pleiades. Oh, well done. Oh, right. Okay. So it's clear that I've got some experts in the audience then. Okay, right, bonus question in that case. Can anybody name any of the Pleiades, any of the stars in this image? That's a real test for you now.
Someone said Pleione.
Oh, Pleione. Oh, wow. No, now I am properly impressed. Yes, if I show you the names of all of them, Pleione is this one here. So either I've got a classics professor in the audience, or I've got a very keen astronomer. So I ask this question quite often when I give talks, and I very, very rarely get an answer to it. But I'm only torturing you. The names of these stars don't matter in the slightest. What I wanted you to look at, though, was the configuration of stars. These are all quite young stars. The Pleiades is a cluster of a few tens of millions of years old. So by looking at a cluster of young stars like this, you might think we could learn about what our own sun was like when it was younger. But there's a problem here. We would really like to be able to zoom into one of these stars and see it as well resolved and in as much detail as we can see our own sun. And I have a beautiful image of our own sun here. This is an image taken with the SDO satellite. It's an image made in high energy lines. So this is the EUV or UV lines. Now, the thing that's kind of puzzling about this image is that you're seeing emission from gas that must be at about 1 million degrees. And yet, I'm sure if I was to ask you, you could tell me that the visible surface of the sun is at 5,000 or 6,000 degrees. But its outer atmosphere, this what we call the corona, is at 1 million degrees. We know that the gas is being heated by the sun's magnetic field. Now, I know that for most people, mentioning magnetic fields is like the kiss of death, but you're just going to have to bear with me on this one. So if you look at this image, let's see if I can get my pointer to work. You see that there's lots of bright emission in a band here, and there's another fainter band in the other hemisphere. In fact, we see the brightest emission over where there are spots at the photosphere, because the spots are where the sun's magnetic field bursts through the surface and heats the outer atmosphere. So this would be our ideal, that we could observe each of these young stars in this amount of detail, and we could learn about what the sun was like when it was only a few tens of millions of years old. But it's really not that easy. We can't resolve the surfaces of these stars. But by analogy with the sun, if the sun has got an outer atmosphere at millions of degrees, it's emitting strongly in X-rays, it suggests that perhaps you need to choose your neighbours carefully if you're looking for habitable stars, because none of these young stars is probably a very good host or very good neighbour for any planets that might be around them. Let's just go back to that image of the sun. I've made it rather larger now so you can see it rather better. You can see these very bright regions here. Lots of UV emission, lots of X-ray emission coming from these, outlining the bands of spots that we see at the solar photosphere. In fact, you don't need a satellite to observe the structure of the sun's corona, however. And by the way, I don't know if any of you managed to see the solar eclipse today. I got a very good image from my living room wall. You can, of course, observe the sun's corona during an eclipse. And here's a little reminder, is Simon, my postdoc down here, illustrating if you want to observe the sun during an eclipse, you really do have to wear decent sunshades. So what are we looking at here? Well, the moon is blocking out most of the light from the sun. You see there's bright emission out in the corona. Some of it looks as if it's formed into loop structures. some of it is forming these radial features here. And you're seeing two different types of structures in the sun's corona. The loops that are very faintly outlined here are loops of magnetic field that are holding in the hot coronal gas. And these almost radial structures are where the hot coronal gas has pushed the magnet, stretched the magnetic field out so that it's almost opened up and there's a wind escaping from the sun. But what I wanted to point your attention to are these reddish features on the limb of the sun. There's one up there and several on this limb here. And these are features called prominences. If I show you another image, you can see here's the disk of the sun here. The prominences are these filamentary structures. You see them dark when they're in front of the disk of the sun, and when they're off the edge, off the limb, you see them bright in emission. So when they're in front of the sun, they're scattering the light from the disk of the sun out of our line of sight, and so they're appearing in silhouette. We know now that these are cool, these clouds. They're only about 10,000 degrees, which is really strange because they're obviously supported in a gas that's at 1,000,000 degrees. Now, by rights, that material should have fallen back to the surface of the sun, but it doesn't because the magnetic field is supporting it. You can see on this other beautiful image here, one of these enormous prominences here. In the process of erupting, it's being thrown outwards from the sun. And indeed, there's a little earth up here just to give you some sense of scale, to show you how enormous these features are. So if I zoom in just on that image, you can see this what looks like a very twisted braided loop. That's the erupting prominence here. You can also see all this bright emission with these loop structures just on the edge of the sun here. This is a huge active region that will be associated with the big sunspot group on the sun. Now, this is a fascinating image on its own, but you shouldn't really think of it as a static image like this, because this is a very dynamic situation. And with any luck, this movie that I'm going to show you will run. I killed the sound because the soundtrack is just terrible. But the movie itself is wonderful. It's a movie of this eruption in progress. You see it being flung out from the corona of the sun. And again, you can see some of the material is in silhouette. It's dark against the background. If you look, you can see this bright pattern of emission now on the surface of the sun, which is the surface response of the flare, the big release of energy that powered this eruption. You can see that even this feature over here is responding to this big flare. It brightens up. In fact, if you look at the limb, you see lots of other loops with flows going back down towards the surface. You get a global image of what is happening here. If you look at the whole disk, you can see the sun as a whole is all responding to this eruption. But if we were to zoom out a little bit, you find even on a larger scale, there is ejection of material from the sun's corona. These are called coronal mass ejections. The material is being flung out from the sun at huge speeds. This gas is at 1,000,000 degrees or so. It's hot, it's incredibly fast. And you can see that it expands as it comes out to fill a huge volume around the sun. Now, this last bit of this little movie is really just showing off. It's showing an image taken from the other side of the sun, from the back side of the sun. But it essentially illustrates the same thing, the response of the large-scale corona to this ejection. So this is the amount of information we can get on the sun today. If I just put together a still image here to illustrate all the points. This is an image in great detail of the disk of the sun with the magnetic loops holding in this 1,000,000 degree gas. This is actually a coronagraph plate that's been put in front of the disk of the sun to block out most of the light. And here you can see the structure of the large-scale corona, with these bright, bright streamers which are being stretched out by the solar wind escaping from the sun. But you know, this is not a new science, really. I've shown you some very glitzy movies and some beautiful images. I'd like you to compare it with this image on the right here. So this was drawn in 1860 during an eclipse. And I reckon that this is a coronal mass ejection drawn here, looking very much like the beautiful image on the left, taken with Soho. And in fact, if you look close to the limb of the sun, you can even see little bright prominences. These would have been pink during the eclipse. And you see these linear features where the solar wind is escaping out into space. So even in 1860, it was possible to observe these features. So why am I telling you about mass ejections from the sun today, when this is a talk about habitability of planets and the impact that stars have on the planets? Or you might think, well, it's because these mass ejections might impact on the Earth. In fact, it's slightly more subtle than that. And it's to do with what happens as this hot gas is thrown outwards from the sun. Here's a little cartoon on the left here. Here's the sun, and here's one of these big loops. It's coronal mass ejection escaping from the sun. And I told you the gas was hot and it was very fast. In fact, it's supersonic, or in a magnetized gas, the equivalent term is superinfinic. So like any supersonic motion coming through a static medium, it drives a shock ahead of it. And you can see the pile-up of material in the shock here in this cartoon. Now, shocks are very good at one thing. They're very good at accelerating particles. And that's what's illustrated in the little cartoon on the right. Here's the shock front ahead of the CME. And the shock is accelerating particles. And it's these energetic particles, when they impact on exoplanetary atmospheres, that's what does the damage. Because the particles are sufficiently energetic that they can dissociate molecules. So if you have an atmosphere with, for example, lots of water vapor in the atmosphere, an impact with one of these energetic particles can dissociate the molecule. The hydrogen is light enough that it then escapes from the gravitational potential well of the planet. The oxygen will recombine on the planet's surface into oxides, and you've lost a hydrogen molecule. You do that often enough, you'll lose most of the hydrogen from, most of the water vapor from your atmosphere. So the particles that are accelerated in the shocks produced by coronal mass ejections are the things that are of concern. Now, I showed you that beautiful movie of the mass being flung out from the sun. But the sun itself as a whole evolves on a time scale of about 11 years. Well, when I say the sun as a whole, that's not entirely correct. Its corona evolves on a time scale of about 11 years because the sun has a magnetic cycle. It has a dynamo that generates its magnetic field, and the dynamo is cyclic. So if you look at the panel on the right here, this is a sequence of images, X-ray images, UV images of the sun, taken once per year. This is the very first one, 1996, is the minimum of the sun cycle. Very few spots on the surface of the sun, very little emission. As we go through the cycle, the number of spots increases, the emission increases as well, until here we have the sun at its X-ray brightest at the maximum of its cycle. Essentially, the same information is shown in the panel on the bottom left. This is the sunspot number as a function of time. So you can see the number rising. There's the peak of the cycle there, and the minimum here back in 1985. And we're currently in cycle 24. What I want to draw your attention to is the panel on the top left. So this is a plot of these energetic particles. So it's number of protons per square centimeter per steradian per second. And you see two quite different behaviors in this plot. You see this low amplitude variation, which is in antiphase with the sunspot number. So when the sun has the most spots, it's most active, this wave here is at its minimum. And then there's another type of behavior, these outliers, these very high fluxes of energetic particles. And this wave has a maximum and a minimum set of phases that is in phase with the solar cycle. So two different things are happening with these energetic particles. And in fact, what is going on is that there are two separate origins for these particles. They come from two entirely different places. The low amplitude variation that we're seeing here is produced by particles that come from outside the solar system. These are galactic cosmic rays. The reason that there are fewest of these at the maximum of the sun's cycle is that the maximum of the sun's cycle is ejecting lots of mass ejections into the interplanetary medium, which makes its wind effectively much denser, and that blocks out some of the galactic cosmic rays. There are far fewer galactic cosmic rays reach the Earth at solar maximum than at solar minimum. These high amplitude events are the ones that come from the coronal mass ejections. And they're to maximum at the maximum of the cycle, because that's when you get the most mass ejections produced. So what happens when this mass ejection gets towards the Earth? And this is just a wonderful combination here. We have a genuine image of the sun here. I think this is in calcium emission or something. Some artist's impressions of the loops that might be attached to some of the sunspots, and a huge mass ejection that's been thrown out from the sun's corona. Now, the Earth is quite a long way from the sun. It takes about 3 days for one of these mass ejections to reach the Earth. And when it does, most of us are very glad that the sun has the Earth has its own magnetic field. So these blue lines are an artist's impression of the Earth's magnetic field with its north and south pole. The solar wind and the mass that is being ejected in it is ionized. So the magnetic field of the Earth does a very good job of deflecting that flow. So most of the solar wind flows around the Earth's magnetic field. So the magnetic field acts like a huge umbrella, if you like, to shield us from many of the ionized particles coming from the sun. But it doesn't shield us from all of them. So let's imagine you've decided to follow a career in astronomy. You decide to become an astronaut. You're out there having your first spacewalk. There you are in your wonderful suit. And there's an alert that there's a huge coronal mass ejection has been detected coming from the sun. Well, okay, you've got 3 days to respond. But let's imagine you didn't spot it at first. You would be very keen to get to some sort of shielded area, because those energetic particles they're not only very bad for molecules, they're very bad for human DNA as well. So in fact, the great joke about the International Space Station, which is the other image, is that when there's a big solar storm, when one of these CMEs is coming towards the Earth, all the astronauts rush into the Russian part of the module because it's the one with the best shielding. It's not just people that suffer during these solar storms. All satellites that have solar panels are at risk because the fast particles damage the solar panels. So most satellites, they will either rotate to turn their backs to the sun, so the back of the solar panel is facing the sun, or if possible, they'll roll their panels in to protect them. So there's a huge industry now in predicting when these storms are going to happen because of their impact on satellites and satellite technology. But what do we see on the Earth when there's one of these coronal mass ejections? Well, we see aurorae. So those energetic particles that come from the Earth, some of them impact on the Earth's magnetic field. There's a complex sequence of events, but eventually some of them are channeled down to come through the Earth's atmosphere. And as they do, they interact with the oxygen and nitrogen in our atmospheres. They knock electrons off of those molecules. And what we see is the resultant emission. I don't know how easy it is to see aurorae from Cambridge. We can certainly see them up here in St Andrews. In the winter, they can be quite impressive. You don't only see aurorae from the Earth, however, you also see them from space. So here on the left is an image of a well-known planet. Here we have big red spots, a bit of a giveaway which one this is. And this blue emission that you see at the pole here is Jupiter's aurora. So this is partly in response to the solar wind impacting on Jupiter's magnetic field, also a little bit to do with Io as well. That's another story. On the right-hand side here is the Earth's aurora as seen from space. So here's the beautiful green auroral ring. The aurora form around the magnetic poles. So northern Canada is pretty much the best place to see the aurora, if it weren't for the ice and the polar bears. And here's another, again, a beautiful image taken from a satellite. And you can see both the red emission and also the green emission. Why am I showing you aurorae? Well, if we could see an aurora on a planet outside our solar system, an exoplanet, it would tell us that that planet had a magnetic field. That would tell us it's a means of shielding its atmosphere from the fast particles from its star. It would also tell us that the interior of the planet was hot, molten, and convecting. So we would get information on the planetary interior that we have no other way of getting at the moment. So there's a lot of effort being put into trying to detect auroral emission from other planets. We've not been successful yet, but perhaps in time, perhaps within your professional lifetimes, it will be detected. So let's go back to my original question. What do you need to make a planet habitable? I've shown you some of the inhospitable things that our own sun does. So let's think of all the obvious things that you would choose if I've asked you what are the factors that you need to make a planet habitable. Well, you need a star to give you light. You need light and heat from the star to get life going. Now, obviously, this image on the right here was taken in Scotland. You can tell that because of the sunshine and the blue skies. I would like to pretend it was my garden, but it really isn't. The other thing that you would also like to have if you want to have a planet that's habitable is you'd like to have liquid water. You want life as we know it. And you'd want an atmosphere. The atmosphere is important not just because life as we know it tends to breathe, but also because the atmosphere acts almost like a blanket. It keeps the surface temperature of the planet in a much more stable state. So you'd want to have a star to give you light and heat, you'd want water on the surface, and you would want an atmosphere. Well, not every planet in the solar system has managed to keep its atmosphere, or indeed keep its liquid water. And, you know, losing one of them is unfortunate. Losing both begins to look a little bit like carelessness. Here we have two companion planets in our solar system, the Earth and Mars. The Earth has water, it has tectonic activity, it has continents, it has an atmosphere, it has weather. And there's Mars. Well, Mars really doesn't have any of those things. Well, not now it doesn't. Mars is now dry, dusty, cold. It has very little atmosphere. It has a negligible magnetic field as well. So what went wrong with Mars? Because, you know, we believe that at one point in its past, Mars did have all those things. It had surface water. It probably had an atmosphere. It had a magnetic field that protected it from the sun. But now it's this dry desert. Well, Mars's main problem really was that it's very small. Here's just a reminder. This image here is actually an image of Mars. Mars, being very small, cooled very quickly after it formed. And because it cooled, its internal convection switched off. There was no longer heat to drive the convection. Without convection, you can't have a dynamo. Without a dynamo, you can't generate a magnetic field. And this image here is of the outpourings from the sun, the solar wind, and a huge coronal mass ejection here, impacting right on the surface of Mars. There's nothing really protecting the surface of Mars now. And any residual atmosphere that Mars has is completely exposed to the sun's outpourings now. So if Mars has such an unfortunate history compared to the Earth, maybe if we want to understand habitability, we have to think about not just how the planets formed and what the composition is and what sort of atmospheres they have, but we have to think about not just what the sun is like today, but what it was like in the past. If you remember, I started this talk off by showing you an image of the Pleiades. The Pleiades, I told you, were young. They're some tens of millions of years old. The sun is 4,500 million years. And the Pleiades, being younger, are much more active. They're like people, they're more active when they're younger. So if, for example, I take you back to the sun and I show you just a beautiful image of some sunspots on the surface of the sun. You can see the center of the sunspot here, the umbra. You're looking down the throat of a big magnetic loop coming up through the surface of the sun. You can also see this wonderful granulation pattern. This is the convective pattern of the sun, which shows you the convective motions that the sun is experiencing. And on the right, again, just some of these beautiful magnetic loops emerging from these sunspots. This is just a reminder of what the sun is like today. And I've shown you lots of the effects that this activity on the sun has on the Earth today. But what about when the sun was younger? Maybe the age of some of those Pleiades. Well, here's the comparison. This is the sun, not actually today, but fairly recently. You see it's two bands of spots. And on the right is an image, a recovered image of a young solar-like star, very aptly named Speedy Mick, because it's rotating very fast. And you see that the pattern of spots on its surface is quite different from the sun. The spots are larger, they cover the whole of the surface, and in fact they go all the way to the pole. We don't see spots at the pole of the sun ever. So this is it's a very good indicator of what the sun might have been like when it was a few tens of millions of years old. If it had this many spots on its surface, imagine the mass ejections that it would have produced. Well, you might ask me, well, do these to these very young suns do they show similar sorts of behavior? Well, remember the prominences that I showed you on the sun that had been drawn in 1860 in that beautiful eclipse drawing. Well, this is a plot that shows where we find prominences around a young sun. Now, the eagle-eyed among you might look at this plot and say, what's on the axes? Well, it's actually velocity. It's a plot in velocity space. And the star is rotating, so you can track features in velocity space. Another simpler way to think about it is this is what you would see if you looked down the rotation pole of the star. So this white disk is the star. These numbers are just the rotation phase. Here's the photosphere of the star, the surface of the star here. And the color here is just gray. It's a rather boring color. This is showing you where the prominences are found. If you think back to that image I showed you of the sun, the prominences are about the size of that little red laser pointer. When we look at this young sun, the prominences are enormous, and they're almost all of the way around. And you notice they're clustering around this red dotted line here. That dotted line is showing you the co-rotation radius. So that is the distance out in the equatorial plane of the star that you have to go before gravity is no longer pulling inwards for you, but centrifugal forces have started to dominate and the effective gravity is pulling outwards. So it's a zero in the effective gravitational acceleration. You can think of it as a gravitational potential minimum. It's a natural place for material to collect. So on these young stars, we find much larger, much more massive prominences. And they don't just sit there calmly in a relaxed and static fashion. Here's another young star. It's a similar plot. The dotted line is the co-rotation radius. And again, the color here, this nice reddish color, is showing the measure of the mass density in the prominences. So this is an image taken 29th of November, and this is one 6 nights later, 5th of December. You can see the overall pattern is similar, but the prominences have evolved. So they are changing on timescales of a matter of days. So I've shown you 2 examples, but they're only 2 examples. There are many, many more that I could have shown you. These features are seen on many different types of rapidly rotating star. So what is it on these rapidly rotating stars, other than the fact that the material is in a gravitational potential minimum? What is it is holding the material in? Well, I thought that I should give you a culturally appropriate analogy here. So this is my explanation for how stars hold on to their prominences. So you have to imagine that the gentleman in the yellow t-shirt is the star, and the iron ball he's swinging around him is the prominence. It's massive, just like prominence, and the chain that he's holding on to is the magnetic field. So as the star spins round, as the guy in the yellow t-shirt spins round, he spins the metal ball around and round and round, just as the star is doing with the prominence. Eventually he lets it go. And when that happens, the metal ball escapes. And this is obviously the point of this, is to see how far you can throw it. In the case of stars, we can imagine that the prominence escapes and it flies away from the star. So if I just show you an image of the sun, here we are, just back to a similar sort of composite image showing the large-scale structure of the corona. Here's a big mass ejection coming out from the sun. Just to put this in context, given the size of the prominences we see on other stars, these are the typical sizes and typical number of prominences that we would see around a young sun. And these are just the prominences, the things that are the little features that we saw at the limb of the sun. You can imagine that ahead of them, there are huge coronal mass ejections. So for planets and their atmospheres that are trying to form around a young star, the existence of these mass ejections must be quite a challenge for them to survive. And you know, it's not just the prominences that are ejected. These stars have winds, just a constant background flow of material. So this is a plot telling us what we knew in 2004 about the winds from stars like the sun. So these are not, you know, 20 solar mass stars. They're reasonably solar-like. And it's a plot of X-ray flux on this axis against, well, this is the wind mass loss per unit surface area. So this is an attempt to compensate for the different sizes of the stars by taking the total mass loss rate and dividing by the surface area of the star. And it's in units of the value for the sun. So a value of 1 on this plot is indeed here where we find the sun. So the sun is losing 10 to the minus 14 solar masses per year in its wind. And these are the other stars for which we've been able to make this measurement. Now, there aren't very many data points on this plot, and it's because it's a very difficult measurement to do. The winds of these stars are very low density. We don't detect them directly. In fact, we only detect them because as the wind pushes out from the star, it carves out a bubble in the interplanetary medium. And at the edge of that bubble, there's a thin shell of compressed gas. And it's by measuring the enhanced absorption of Lyman alpha photons as they come through that shell that we infer the mass loss rate in the wind. So I'm going to have a little detour into scientific sociology here. Here we have what looks like a beautiful correlation. In fact, you can see there's even a nice straight line drawn through the points with some sort of error bar. And it looks quite convincing. You would say that stars that have a high X-ray flux, they're therefore very active, they're probably rotating very rapidly, have very powerful winds. So the sun is away down here, it's reasonably old, reasonably inactive star, and the sun when it was younger was probably further up along this line. But this was 2004, but then this particular team went and they did something that you should really never do once you've got a nice correlation like this. They went and got more data. And, you know, there is such a thing as too much data, because what they found was something a bit puzzling. When they observed some more stars, they found they didn't lie on this nice line. Here's one called EV LAC here, well below the line. Pi 1 Yuma, again, well below the line. In fact, it's almost on a par with the sun. And Xi Bu A and B, it's a binary, so there are the 2 component parts shown here. So what happens to the right of this diagram? You know, is it that as you go to the very most active stars, they produce lots of X-ray emission, but no wind or very little wind? Does this line stop? Does it flatten off? Well, the authors decided to hedge their bets, so they drew what they called a wind dividing line. And they said, on this side, we've got a nice correlation, and on this side, we've got dragons. And this was the situation for quite a long time. We couldn't get any more observations in this region of parameter space. These are very active stars. So we just weren't sure that this would represent the region of parameter space of the very youngest sun, probably the time when we're most interested, but we didn't have any measurements. But then we realized there was something rather clever that we could do. We could use the prominences. So here's a little cartoon of a rotating star and a big magnetic loop here, holding in gas, and a prominence trapped in its summit here. Well, we know how long the prominences live for because we observe from night to night, And I showed you that prominence system evolving on a timescale of a few days. So we know the lifetime of the prominences. We can get their masses by looking at how much they absorb the light from below them. So if you take mass divided by time, you get a mass loss rate. And this gives us the rate at which material has flown up the foot points to form this prominence. So by observing the prominence, we get a measure of the mass loss rate. And this opened up this region of parameter space for us. So here's a more recent version of the same diagram. I've just put the names of all the stars on it. Here's the sun in yellow, which is still mass loss rate against X-ray flux. And these blue points are the points that we now have measurements of the mass loss from these stars using their prominences. And what we found was that the correlation carried on beautifully. It's just that there's a lot of scatter. But you know, that's something that we can live with, I think. So where are we today in modeling this? Well, we can model the winds of these stars. This is a model due to Alini Vidotto on the surface of the star. Color is showing you the radial component of the magnetic field because we can map magnetic fields across stellar surfaces. And the grey lines of the model, you see some of the magnetic field lines are loops. They're holding in the hot gas. And some of them have been stretched out to be almost straight by the gas escaping from the wind of this star. We can also model the locations of prominences. The red blobs here are the prominences that are trapped on the magnetic field lines, a little bit like iron filings that would be trapped on the field lines of a bar magnet. So when we look at these very young stars, we are now in a position that we can understand the winds and the mass ejecta much more than we did 10 years ago. But what we would really like to be able to do is to follow this evolution over the lifetime of, for example, the sun, to understand how the sun's activity changed over time. So I can illustrate this for you. These are actually models that are reasonably well supported by data. So this is a plot of the age of the system on this axis in millions of years. And on this axis is the angular velocity of the star's spin rate in units of the value for the sun. Now, I told you the sun was 4,500 million years old, so it's a way over on the right-hand side here. So the three curves are for three different example stars. And this one started off when it was very young, rotating very slowly. This one was a middling rotation rate, and this one was rotating very fast. But they all show roughly the same sort of history. They start off with their rotation rate is constant. And that's because they're young enough that they still have a huge disk around them in which their planets are forming. And the magnetic field of the star is reaching out and linking through this massive extended disk. And this controls the rotation rate of the star. So even though the star is contracting as it forms and therefore should be spinning up, the effect of the disk keeps the rotation rate constant. But eventually the disk is all used up. All the planets have formed, all of the material has fallen onto the star to make planets. The disk is gone, so the star spins up as it contracts. And it spins up and it spins up until eventually it's generating so much magnetic field, it's powering such a powerful wind that the wind, of course, doesn't just carry away mass, it carries away angular momentum. And the wind starts to spin the star down. So the rotation rate of the star slows down over time until it's way over here, rotating only very slowly, like the sun. So this is the history, the rotational history of a star like our sun. And I showed you for the sun today what its activity was like and what impact that has on the present day Earth. So if we were to look back in time when the sun was much younger and it was rotating much faster, what might we have inferred about its effect on the planets around it? Well, let's take a little tour through time in our solar system. This is a similar plot. This is time on this axis in millions of years. Here's the Earth today. This is actually the pressure of the solar wind. It's giving you a measure of how, what the impact of the solar wind on the Earth's magnetic field would have been. It shows broadly the same sort of behavior. So let's look at the very early solar system. What was happening in the early solar system? Well, if we look back to the first 10 million years when the sun was spinning up and becoming more and more active with time, that's when the giant planets formed. So Jupiter, Neptune, Uranus, Saturn, they all formed in this early, very active period. Thankfully, they're a long way out from the sun, so maybe they didn't care too much. The little rocky planets formed rather later, and that's probably a good thing for them because at the point where they formed, the sun was already starting to spin down. Its X-ray luminosity was dropping, its spin rate was dropping. And so here we have the inner planets. Mercury, Venus, a molten Earth, a very young Earth here, and Mars as it is today. Well, that was Mars as it is today. Here's an image of Mars busy losing its remnant magnetic field here as the solar wind sweeps past it. So this is a rough date by which we thought Mars lost its magnetic field. It cooled and its dynamo switched off. And the atmosphere disappeared not very long afterwards. There was also something very dramatic happened in the early solar system at about this time. It was something called the Late Heavy Bombardment. And it was a period in the history of the solar system where there was a huge number of asteroids were flung into the inner solar system. Something happened with the dynamics of the orbital dynamics of the planets that destabilized a lot of these asteroids in their orbits, and they impacted on the inner solar system. Almost certainly, a planet that might have had life before this point wouldn't have had life afterwards. You can see when you look at, this is an image of the moon, and you can look at the cratering on the surface of the moon. It's the fossil remnant of the late heavy bombardment. So that's probably the earliest point at which it would be possible to have life in the inner solar system. What about after that point though? Well, let's go back. Here we are, we're just over 1,000 million years old now. This is the first measurement we have, first evidence of the existence of the Earth's magnetic field. And that's important because that's probably the point at which the Earth was capable of protecting a young atmosphere if it had one. Well, it's a little bit later, getting quite close to the present day, when we have evidence that the Earth has developed an oxygen-rich atmosphere. So these are all the stromatolites getting going, producing oxygen in the Earth's atmosphere. So this is the timestamp at which we believe life was asserting itself on the Earth. And look at how much happened in the solar system before this point. There was a huge amount went on. However, it's probably just as well that it took a long time before life got going, because at least at this point, the sun's rotation rate has almost spun down to its present day value. The pressure of the solar wind has dropped by 3 orders of magnitude. So the impact of the sun's activity on the Earth is so much reduced. If life had been trying to form on the Earth at the peak of activity back here, at 10 million years, or maybe around the age of the Pleiades today, it perhaps would have been a very different story. So I want to leave you with a final thought, that habitability isn't forever. When we think about looking at habitability on other planets around other stars, we should bear in mind that it's not just enough that your planet is habitable at the time when you observe it, For life to form, it has to have been habitable for a reasonable amount of time. And in our own solar system, we have winners and losers in habitability stakes, and Mars is sadly, clearly a loser. But I have now talked for absolutely long enough, so I'm going to leave you with my favorite cartoonist in the universe, Larson, because I expect all your brains are probably completely full too. So I'm going to stop and I'm going to see if you have any questions for me. Thank you.
Thank you, Professor Moira Jardine, for this wonderful talk. Now we move on to the Q&A session. If anyone has questions, they can just put it in our group chat.
And I'm going to see if I can switch off my pointer so that so I can hopefully get a proper pointer back, which means that perhaps I can see the chat window. Maybe. Yeah, okay. Oh, somebody was having trouble with the sound. I'm sorry about that. Maybe you managed to get the captioning to work.
Yeah.
Yeah, you can either put a question in the chat, or if you simply ask, Lehan, I'm sure will repeat it for you.
Oh, you can just unmute. I don't think I... Oh, there is a question.
Oh, that is an excellent question. I love the skiing picture, by the way. Thoroughly approve of that. For human causes, I don't think I'll be drawn on that one. From astronomical ones, there is actually quite a bit of work on looking. There's a wonderful paper, and I don't know if they're allowed to keep the title, but the original title was The Last Puddle on Earth, and it was looking at the evolution of water on the surface of the Earth as the Earth ages. And obviously, as time goes by, the sun is going to brighten and expand, and at that point the Earth will almost certainly not be habitable. So whether we've got another 4.5 million years, I don't know. I suspect that the astronomical causes will pale into insignificance compared to all the other ones. Oh, that's a good question. So if you haven't got the chat window up, it's asking about 61 Sig A, and had we looked at 61 Sig B? No, the 61 Sig A is by far the more popular to look at. In fact, not only have we mapped the magnetic field across its surface, but we have a complete magnetic cycle for 61 Sig A. So it is really a poster child for studying the magnetic fields of other stars. 61 Sig B, we haven't mapped. I'm not quite sure why it's less popular. It might be that it's a good deal fainter. But yes, 61 Sig A is definitely everybody's favorite. You're very welcome. I'm glad that nobody is asking me if I can reel off the names of any of the Pleiades.
Okay, if there's no further questions, I guess that's all we have tonight. Thank everyone for being here. I hope you all have enjoyed our talk. And thank you again to Professor Moira Jardine for sharing your knowledge with us. And good night to everyone. And I hope to see you guys again in person next week.
Okay, good night, everybody. Thank you for listening. It was fun to talk to you. Maybe
Bye.
next time it will be in person.
Yeah.